Hello everyone, I will explain about the jet engine, that is a turbojet type of engine. So there are different types of aircraft engine like turbopropeller, turboshaft and turbojet engine, right? So I'll focus only on the turbojet engine. The different components are shown here. Let's say this is a compressor, combustion chamber and turbine. So what happens in this case? So basically air compresses. As soon as we starts the compressor, okay, so air starts to compress in this component, and air compresses at high pressure and velocity that goes into the combustion chamber. In combustion chamber, what happens? That air mixes with the fuel, okay, and at a certain air fuel ratio, combustion occurs and it produces the hot gases. And that hot gases at high pressure goes to the turbine, and this turbine expand these gases, expel these gases to atmosphere. So where doing the work in the turbine, it produces energy. Since it produces the energy, this shaft of this turbine is connected to the compressor. So on single shaft, these two components are placed. So that's why whatever the energy is produced by this turbine will be utilized to drive this compressor. So we can say that this is a self-sustaining engine because in this case we don't require external power. Okay, after producing the work, that work will be utilized to drive this compressor, and will stop the external energy which is provided to the compressor initial. Okay, so after expelling these hot gases to atmosphere, that goes to atmosphere. This is simple open Brayton cycle. But in case of a jet engine, we employ one component, that is nozzle. You can see here, this is nozzle. Okay, so nozzle, what is the function of this nozzle? That nozzle converts the high pressure gases into the high velocity gases. At the expense of this pressure, we get the high velocity at exit of the nozzle. Hence, we employ that component at exit of this turbine, and hence we get the high velocity, right? So at higher velocity, that produces the thrust effect. Okay, so at exit we get the high velocity, and it produces the thrust, and this thrust is utilized to propel the engine, that is jet engine or the turbojet engine. The efficiency of each component is very important to produce the thrust efficiently. Okay, so that's why we need to study each component separately. Okay, so for compression, here is the isentropic compression happening. Okay, ideally we are considering isentropic, that is reversible adiabatic process, in which I can show here to it obeys this isentropic law, PV raised to gamma equal to constant. Let's say, so isentropically it compresses air, goes to combustion chamber where combustion is occurring at constant pressure. Let's say pressure is constant. Okay, we are ideally considering these things. And after that, hot gases goes to turbine. Again, turbine obeys the same law, PV raised to gamma equal to constant. Isentropic expansion is happening here, right? In nozzle is the reversible adiabatic nozzle. It produces no energy and no work, right? It does not consume any energy as well, right? So we'll consider it as a reversible adiabatic thermodynamic system, let's say, right? So hot gas in, let's say this is hot gas in, hot gas out, which produces the thrust. So you can see 1 to 2 here. 1 to 2 is the isentropic compression process where entropy remains constant. 2 to 3 is the constant pressure heat addition. Heat is being added here because fuel and air mixes and produces the hot gases. Combustion occurs. 3 to 4 is the expansion gases at isentropic. That is a constant entropy process, and these gases expel to the atmosphere. You can see the actual schematic of the experimental setup. So I will separate this total experimental setup into two components. Let's say this is first component, jet engine, and second component is the eductor nozzle or mixing pipe. So this is the jet of the exhaust gases produces at the exit of this jet engine. Okay, and hence the thrust is produced. Okay, so jet is going in this direction, so it produces the thrust in reverse direction. So this is thrust produced in this direction. Hence the propelling effect is produced, and engine is moves in forward direction. Okay, so that obeys the Newton's third law of motion. Okay. To cool down this engine effectively, we increase the heat transfer rate by providing this eductor nozzle or mixing pipe. This is simple venturi, you can say that. Okay, so this is simple convergent section and throat section, and gases are expanding here. So this is divergent section. So we can say that this is a venturi type of section is provided over here. So which produces the Coanda effect, right? So let's say this is Coanda effect. Due to Coanda effect and second is of the energy or the momentum of this jet. Let's say this is momentum energy. Okay, so because of these two effects, what happens here? Whatever the air starts to flow from atmospheric condition, and that Coanda effect is basically is what this is which creates the flow which sticks to the surfaces, right? So the flow sticks to these surfaces, and hence this flow occurs like still along this jet, and hence there will be the cooling process of this jet engine. So at the exit, these hot gases are cooling down with the mixing of this atmospheric air, and hence it produces this streamline like this. So hence it cools down this engine. So externally it is cooling as well as internally it cools down. Okay. So this way we uses this mixing pipe effectively by providing at the exit of this jet engine. When you can see here the experimental facility we have. This is a small jet engine. Okay. So as I told you earlier that this is categorized into two components, like one component and two components. So one component is gets rid of jet engine, which contain different components like compressor, combustion chamber, and turbine and nozzle, right? And this is mixing pipe or reactor nozzle.